So A equals A sub 0 e to the kt. It looks like a mess, but during your virtual module, we looked at compound interest and we looked at the continuous interest formula, A equals P e to the RT. And do you remember the different parts of that? P is the principal, what you're investing in the account. E is the constant 2.7. R is the interest rate. And T is time, so how many years. This formula is just being applied to other things like radioactive decay, population growth. See, the A is the same. Instead of calling it principal, they're calling it A sub 0. So the initial insect population or the initial temperature of the pizza or whatever the initial thing is. E is the same. Instead of R for interest rate, they use K for constant. K is the population growth or whatever it is. T is still time. So it really is just the continuous growth formula that you've already seen. So you've already done this, manipulating this equation. So this is just saying what I just said. A sub 0 is the original amount. K is constant. T is time. Oh, this is important. If K is positive, it'll be an increasing function. So population growth, K would be positive. If K is negative, it's decreasing. So radioactive decay or temperature going down, your K value is going to be negative. Classic examples, compound interest, unlimited population growth in simple organisms, decreasing, radioactive decay, carbon dating, car depreciation. Simplest applications, you know A sub 0, K, and T. So example 1, you're just using the equation and plugging in what you know. So they're giving you the population growth is 500. That's the starting value of the insect population. E to the 0.02 T. 0.02 is the growth rate. I'm going to plug in T. Now T says it's in days. What am I going to plug in if the population has been 1 week of time? Just 7. So you're just plugging in a number into this equation. So 500 E to the 0.02 times 7 days will give you the new population of the insects. So practice typing it into a calculator. If there's not one under your desk, go grab one off the back table. You want to practice typing these in today to make sure you know how to do them. So someone type it in and give me the population of the insects. Yeah, 575 with a little bit of a decimal, but that's good enough. Anyone not able to get that on their calculator? So if you know the starting population, if you know the growth rate, and you know how long, this is just a formula to figure out the new population. Sometimes we know the values of our new population. So what is the final growth? We know K and T, but we have to solve for the initial population. It may look intimidating, but E to the KT is just a number. So here's another type. So now you're going to be given different information. The size of an insect population has reached 10,000. A researcher has determined the value of K is 0.05 as the growth rate. What was the population 3 days ago? People were studying coronavirus like this. There's 100 infected people in China. If it's growing at this rate, when was the first case? Oh, was it November? Was it September? Right? They were trying to figure out how far back the virus started to spread. It's just the same type of science. So currently the population is 10,000. We want the initial population. So A sub 0 is just a variable. That's not the number 0 that you plug anything into. A sub 0 is like X. And then we've got E, and 0.05 is our K value, and it's been 3 days. What was the starting population? So you could guess and check. It has to be less than 10,000, right? Did it start at 7,000, 2,000? So what it's telling you here is that this is just a number. So 2.7 raised to the 0.05 times 3, that's a number. So if we can evaluate that number, all we have to do is divide 10,000 by that number to solve for A sub 0. So it's basically figuring out what you're plugging into the equation and then how you're going to solve it. So take e to the 0.05 times 3, then take 10,000 and divide by what you just got. You should get a number that's less than 10,000. So if someone gets it, tell me what you got as your original population. No? 8,607. But did you get that number? Oh, dividing itself. Okay, yeah. So here's what I did. I took 10,000 and divided by e to the 0.05 times 3. So make sure that when you're typing it in, you're getting this answer, because if not, you're missing a divided by or a parenthesis or something. So you want to be confident using the calculator to get your answer. So 8607, about. So in 3 days, our population went from this to this. So it's just being kind of fluent with where am I plugging things in? You know, how do I solve? This is kind of like level 1. I haven't solved for any exponents yet. So level 2 is now I'm going to start either solving for k or solving for t. As a scientist, they have to solve for k. They don't know the growth rate in China versus the United States versus in a monkey population versus in the desert in the insect population. So it's important as a scientist to be able to solve for k. So here's where logs come in, because they need to solve for k. So the most common problems involve finding the value of k. The process of carbon dating involves finding the value of k. So whether you find this molecule, whether it's a fossilized leaf or a bone or something in the ice versus under the ground in New Hampshire or California, the k value for carbon dating might change. So here's my example. So a fossilized leaf currently contains 30% of its normal carbon-14. How old is the leaf? This is a two-part question. I don't have an equation yet to be able to solve this. Here's the first part. The half-life of carbon-14 is 5,600 years. Have you ever heard of a half-life before? So a half-life, as an aside here, so a half-life, if I start with like 10 grams of whatever material I'm talking about, after 5,600 years have passed, I only have 5 grams of it left. And then after another 5,600 years, now I have 2.5 grams of it left. I have half as much every 5,000 years. So it takes a long time for it to go away, because you still have half of it left. Oh, you still have half of it left. You still have half of it left. So it takes many half-lives to get down to an insignificant amount. So it says first we have to find the value of k. I think of half-life when I'm finding k. So if I start with like 10 grams, I'm ending with 5 grams. I'm picking an arbitrary number. I picked a number to start with and I just cut it in half. You could pick 150. You could pick starting with 2, now you're down to 1. So E, I don't know k, but I know that it took 5,600 years. So I have to make up my starting and ending values to represent half-life. I know E, I don't know K, and I know it took 5,600 years. So how would I solve this equation? What would be my first step? So I need to get E by itself. So what would be your first step to get E by itself, do you think? Algebraically, what's your first step? Just like we did on the warm-up. I want to get this by itself. So what do I do? Divide by 10 on both sides. So I have 0.5 equals e to the k times 5,600. So I'm ready to change form into log form to solve for this exponential problem, right? So what's log form of this? Log base e, right, which is natural log, of 0.5 equals k times 5,600. Are you with me from there to there? Because that's the hardest step of this whole process. E is the base. The 0.5 goes inside the log, and that frees up your exponent over here. So if I reread this, e to the k times 5600 equals 0.5. So this is a value, right? This is the natural log of e on your calculator. So natural log base e is ln. So I'm going to do ln of 0.5, and then at the end, divide by 5600. K comes out as a really small number. Take the natural log of 0.5 and divide by 5600. I get this with this little e, meaning scientific notation, to the negative fourth power. So what that means is sliding your decimal place 4 places to the left. So if I was going to write k out, it's negative 0.00012. That's what this means. Negative 1.2 times 10 to the negative fourth is negative 0.00012. I did all that work just to solve for k so that I could use k in this problem. So then part 2, so this is like, it's an application problem. It takes a little bit of grit to get through it. There's k. You can kind of remember this process though. All we took was the natural log of a half and divided it by the half-life. So if you kind of remember that process, there's a shortcut for you, but don't have to memorize that. I'm going to plug k in up here. So it says now we can use this formula. 0.3 equals e to the kt. Where's this 0.3 coming from? 30% of carbon 14. So originally, remember, it was 50% for half-life, so we represented that by 0.5 e to the k times 5600. They're jumping ahead and they're saying, okay, I have 0.3 for 30% equals e to the kt. So they picked a number here, like 100, and put 30 and divided and got 0.3, just like we did 10 and 5, divided and got 0.5. So I'm going to do 0.3 equals e to the negative 0.00012 t. So you have to solve this for t. The same way we just solved the other problem for k. E is already by itself, so I'm going to change into log form. Log base e of 0.3 equals negative 0.00012 t. So you're going to take the natural log of 0.3 and divide by the k value. You're going to see that that's the case a lot. You're always taking the log of this and dividing by the constant. So you're going to take the natural log of 0.3 and divide by the k value. I like using the full k value on my calculator, so I'll hit divided by and then I'll arrow up and I'll just grab that full entry. I don't know how much it changes your answer by. Well, it changes it by 1,000 years or 300 years. So if I use the exact k value, which is what a scientist would use, how old is the leaf? 9,700 years. If I use the rounded k value, how old is the leaf? 10,000 years. I mean, I guess it's semantics, but I like using the full value when I can. So t for that problem is 9727. Okay, so that is the most challenging problem that you'll have, having to solve for k and then having to solve for t. So there'd be like maybe one question like that on a test. I'm not going to dwell on this for the whole test. This is like at the end of understanding logs, if you could do one problem like that, you should pat yourself on the back, because that's some of the hardest algebra that you'll see this year in pre-calculus. So we're going to do more practice on that. So I get it. You probably don't understand all these steps. We're going to do more practice on that. So before we go for a walk, I'm going to show you Newton's law of cooling, which is another complicated equation. I would give you these equations on a test, so I would give you all that information. You don't have to memorize it. Just like I would give you, this equation, I would give it to you on the test. All you have to do is be able to use it. That's hard enough. So Newton's law of cooling, I think, is interesting. Those of you that work in a restaurant, it's very relevant in restaurants when you want food going out at a certain temperature. Or when you're cooking, you might have to cool whatever it is, your base or your stock or your pie filling to a certain temperature before you either add other ingredients or cook it. So Newton's law of cooling, it allows you to figure out the cooling rate for a liquid and then apply it. So here is this complicated function. Capital T represents room temperature. U sub 0 is the starting temperature of your liquid, or whatever it is, pizza. There's that capital T again. E to the K is a constant, and lowercase t is time. So if Danny boiled water for tea, and after waiting 3 minutes, he took the temperature of his tea, it was 60 degrees Celsius. This also works for Fahrenheit. This problem's just in Celsius. If he likes his tea at 40 degrees, how long should he wait before drinking his tea? And assume room temperature is 21 degrees Celsius. Our room temperature is like 70 degrees Fahrenheit. So this is just a Celsius version. You'll do a Fahrenheit version next. What temperature does water boil at? Do you know for Celsius? Nope. Celsius is 100, and even 100. That's where Celsius is different than Fahrenheit. Fahrenheit, I think, is that 312? Might be 312. We should find this out. Oh, 212. Did you know that? Okay, so 212 Fahrenheit is 100 degrees Celsius, and 20 degrees Celsius is 70 degrees Fahrenheit. There's that conversion factor, the 9/5 C, right? Anyway, you don't have to convert. We're in Celsius. We're going to stay in Celsius. Okay, so this U of T is the current temperature of the water, right? After 3 minutes, the temperature of the water is 60. So the first part of my equation is the water is currently 60 degrees. What is room temperature? 21 degrees. What was the starting temperature of the water? 100. So then it tells me to subtract room temperature again. So 100 minus 21 goes in the parentheses. E is just E. K, I don't know for this T. T-E-A, I don't know it for this problem. He waited 3 minutes. So after 3 minutes, the T cooled from 100 degrees down to 60 degrees. So your first step is to calibrate K for this instance, because his tea cooling in a cup, he might be using a styrofoam cup or a coffee mug. He might have it in the refrigerator versus on the kitchen table versus standing outside, right, in the cold. So obviously it's going to cool at a different rate based on what it's in, where the person is standing, all those things. So you've got to calibrate it first, and then you could calculate how much longer he has to wait. So do the algebra with me. First, you would do parentheses. What's 100 minus 21? 79, right? So this number right here is 79 e to the k times 3. This is a multiplication part. This 21 is freely separate, right? So the first step is to subtract 21 to the other side. And then this 79 is going to get divided to the other side. So what's 60 minus 21? 39. So I have 39 equals 79 e to the k times 3. I subtracted 21. Now I'm going to divide by 79 on both sides. So this is a fraction. I wouldn't round it. I would just leave it as a fraction. And then that is equal to e to the k times 3 power. So to solve for k, we have to switch forms into log form, right? So my log is base e of 39 over 79 equals k times 3. See how the e is the base? Raising it to the k times 3 power gives me 39/79. I'm going to evaluate this on my calculator and divide by 3. So that's the natural log of 39 divided by 79. Gives me a number. And then at the end, I have to divide that number by 3. So what does someone get for K? Take the natural log of that fraction, hit enter, and then divide by 3. You might have to put this fraction inside parentheses in the log. I didn't try it without parentheses, but did someone get a K value? It's a negative number. Yeah, what'd you get? Yep. Negative point, we'll say 235. How about that? All right, I still don't know what temperature the T has to cool to, right? All I did there was I solved for K. So I'm not going to do it for you. I'm only going to give you like one problem on a test where you solve for K and use it, but these are 2 different times you'd have to solve for K. All right, let me set up the next part of the problem for you. How much longer does he have to wait? He wants the T to be 40 degrees, right? 21 stays the same. The T is currently 60 degrees. I know the cooling factor, negative 0.235. I need to solve for T. So the 40 is what I want. 21 is room temperature. The 60 is currently the temperature of the T. I know the cooling factor. I need to solve for little t. Try to solve it the way we just did it up here and see if you can get your T for your number of minutes. So I'm going to give you a minute to at least try it on your own first. Let's see, when you subtract, you'd get 19 over here equals, is this 39? I don't want to make a mental mistake here. Okay, negative 0.235 T, divide by 39. So you're ending up to take the log base E of 19/39 equals negative 0.235 T and dividing by negative 0.235 at the end. Is that kind of what you did or tried? And if you think about kind of half-life, but cooling, it went from what? 100 degrees down to 60, which is about 2/3 of the temperature. Then it has to go from 60 down to 40, which is about 2/3 of the temperature. So shouldn't that cooling take about the same amount of time? So it makes sense. When you take the log of this number and divide by negative 0.235, you do get about 3 more minutes. So 6 minutes initially or 3 additional minutes. Make sense?